Yeah, thank you so much, Henrik, and thank you for running the workshop. And it's my pleasure to be here. I come to you from Hawaii or wherever this is, Caribbean, in my dreams, to talk about scalability in autonomous driving workshop in autonomous driving, especially with respect to how we see it at Tesla. Okay. Yeah, so I'll tell you a little bit about Tesla Autopilot, the product that we're sort of building at Tesla. And then I'll talk a bit about some of the networks that we have in production and some of the new networks that we're developing for full self-driving, and what they look like and how they're different. So first, this is a scalability workshop. I think no one has quite scaled autonomy as much as Tesla has. So we have a massive fleet, of course, that is global. In the entire world, we have roughly the fleet size of 1 million cars out there. These are internet-connected devices. And we sort of receive data from them to improve the autopilot and, of course, ship autopilot wide to all these countries. So it's a really massive scaled product. Now, these are somewhat outdated numbers, but I think the intention with these slides is mostly just to communicate again the scale of the product. People have driven autopilot for billions of miles. Some of the products that we currently support in production are features such as Navigate in Autopilot. Well, of course, the core autopilot will keep you in your lane and keep the distance away from the car in front of you. Navigate in Autopilot is a functionality that allows you to basically point to an arbitrary point in the world. And then as long as you stick to the highway system, the car will do all the right lane changes and all the right forks to get you there. So this works quite nicely. We also have Smart Summon from late last year, where you can summon the car to you in the parking lot using your mobile app. So the car comes out of its parking spot and comes find you. Recently, about one and a half months ago or so, we released Stops on Autopilot. So what this does is there's a crop here from the instrument cluster and showing sort of like a zoom into the user interface. And here we see that the car is registering all the traffic lights, all the stop signs, stop lines, and everything else that is needed to sort of figure out where the car should come to a stop in the world. So we're sort of breaking up the entire problem of autonomy into small pieces, and then we're trying to sort of solve them one by one and release these to customers along the way. So in this case, we've released some of this functionality for recognizing traffic lights. In this case, we have 2 red on the left and 2 green on the right. We recognize them. We understand not just that they're green and red, we actually understand which ones are relevant to your current direction of travel. And that's actually the much harder problem, by the way, not just recognizing this green traffic light. It's whether or not this green traffic light applies to you that makes this an extremely difficult challenge. Under the hood, even if the autopilot is not active, we have a lot of active safety features. So for example, automatic emergency braking, front collision warning, lane departure avoidance, and so on. So these always work under the hood, monitor the environment in 360 degrees. And if anything as bad is about to happen, we either beep or slow and so on. These features work really well. So I believe Tesla Model 3 actually achieved the highest ratings for safety assist. And we also did really well in vulnerable user detection. These numbers are somewhat abstract. So what I like to show is exactly what we're talking about with respect to what this technology is doing on the roads right now in production, and how it's actually basically preventing really bad accidents from happening. So here, this person was not paying attention. I think the driver was not paying attention either, but we were able to detect the pedestrian, of course, and slam on the brakes when it was appropriate. Here's another video. This person on the left is not paying attention. The car will slam on the brake. Here's one more. They get somewhat pretty crazy. So there's a person walking from the right. Lots of occlusions. We will slam on the brakes. So we see lots of these actually every day, tens to hundreds. Not all of them are true positives, but a good number of them are. And this is where sort of detection really counts, because this stuff is running on people's cars and actually making a difference. Now, our ambition, of course, is to produce full self-driving, so not just stopping or taking forks on the highway and so on, but getting people from point A to point B arbitrarily. So your pin is not just on the highway system. Your pin can be arbitrarily placed in the world, and the car will sort of do all of its right turns. It will take all the forks. It will stop for traffic lights and so on. So here the car took a left and on this intersection, and we're coming down towards the highway, merge on the highway, and continue and so on. Now, the thing I like to point out always, because it's not clear if you're just a bystander looking from outside in, Here's a video I have of Waymo doing a very similar maneuver. It takes a left on this intersection. And even though these two look the same, under the hood, of course, they're completely different. And that has to do with how we approach autonomy. So, of course, Waymo and many others in the industry use high definition maps. So you have to drive first with some car that pre-maps the environment. You have a perfect LiDAR map that you localize to with a centimeter level accuracy, and you are on rails. You know exactly how you're going to turn through the intersection. You know exactly which traffic lights are relevant to you. You know where they are positioned and everything. We do not make these assumptions. So for us, every single intersection we come up to, we see it for the first time. We have to figure out what does the intersection look like, which lanes connect, which traffic lights are relevant to you. Everything has to be solved kind of on spot, similar to what a human would do in this kind of a situation. And speaking of scalability, of course, this is a much harder problem to solve. But once you actually do solve this problem, there's the potential of actually beating this down to, again, millions of cars on the road. Whereas actually building out these LiDAR maps on the scale that we operate in, with the sensing that it does require, would be extremely expensive. And of course, you can't just build it, you have to also maintain it. And the change detection of this is extremely difficult. So Alex showed some example from this morning in the UK where things are blocked off because of all the COVID social distancing and so on. Your lane graph has changed. And so you have to just dynamically respond to it. You can't just afford to rescan all of these environments all the time. So that to us is not a scalable approach, and it's not the one that we employ in our approach. So just to give you a sense of what these networks look like, the ones that we do have in production, of course, they need to solve a lot of visual recognition tasks. So they have to detect all these traffic lights and lane line markings and static objects and all kinds of things like that. There are actually two customers for all of these predictions. Number one is the planning and control module that tries to wind its way around all of these environments. Number two is the instrument cluster. So we like to show people as much as possible on the instrument cluster to give them sort of some confidence that the Autopilot is doing the correct thing. So these detections are very useful for that as well. This is a video that we sort of produced recently for a web page we put together, where the car sort of we're showing some of the raw detections that the Autopilot has to make. So you saw stop signs, stop lines, traffic lights, cars, cuboids, lane line markings, curbs, static objects. There's a trash bin over there. What's not shown here is a lot of other things. So every one of these lines, actually, we know whether or not it's a parking line, as an example. So that's an example of an attribute of a line. We know that these are crosswalk lines and so on. So those attributes are not actually even shown here. There's tons of predictions under the hood here. They all have to work correctly. Now, these predictions are actually really hard to achieve. So even for a very simple case like a stop sign, you would think that a stop sign is a very simple thing. I mean, we've solved much harder visual recognition problems. ImageNet recognizes thousands of categories. So why would stop sign be any difficult? And actually, when you try to actually scale this up again and deploy it wide, you will come across lots of variations of even the simplest stop sign. So stop signs can be on walls. They don't just have to be on poles. They can be temporary and on various kinds of signs. They can have these flashing lights associated with them. They can be held by a person or on top of a pole. They can be occluded heavily by foliage. They can be occluded heavily by signs, by cars. Actually, these stop signs are part of cars. And of course, they can be in an enabled or disabled state. So you have to pay attention to that if you want to actually respect it in your driving policy. Held by people. They come with all kinds of modifiers. So these stop signs don't just apply all the time. They might apply only if you are going right, or if you're going left, and so on. So you have to actually recognize these modifiers because, again, we actually drive on vision. So we need to detect this and do the correct thing at the time that we're there. That is not to say, by the way, that we don't use maps. We do build maps, and we use all kinds of fusion between vision and maps. But our maps are certainly not centimeter level accurate. So we do not know the exact metric distance to the leaf on the tree over there, but we do the stop sign applies only when the gate is closed. This one only when the arm is down instead of raised. This stop sign only applies in the action conditional case of turning to the left. So here we have to actually ignore the stop sign if we are going to the right. Now, in order to get all these detections to work, we employ what I call the data engine. And so basically the rough idea is you have to, at scale, the name of the game sort of that we play all the time in a team, and this is the bread and butter of what we do, is need to at scale massage and curate this data set so it has all of these cases in it. Otherwise, your network has no chance. So I believe we currently have probably the largest data set of stop signs occluded by foliage. We have the largest data set of except right turn for a stop sign. And these are all real data, of course. We don't actually utilize simulation all that much. Our bread and butter really is we have 1 million cars out there. They can send us triggers in arbitrary conditions that we specify. And how do you very quickly build out a data set of stop sign occluded by foliage? And that's the kind of problems that we're solving. There's not a lot of sort of like research on that. But for example, starting with just very few stop signs occluded by foliage, we've developed techniques to boost the amount of that kind of data in our data set. So starting with maybe 10 of these, we could develop a classifier that detects the issue, and then we can ask the fleet to, when they're driving around, look for that possible thing occurring. And when a classifier thinks that it might be occurring, it will send us images. So we do that all the time. Of course, talking about scalability, this is not just in the US that we care about these stop signs. So these are Chinese signs, Korean signs, Japanese signs. They come with their own modifiers. They have their own challenges. They have their own rules of law and how they should be handled. So this becomes a very heavy sort of project to actually get something like a stop sign feature to work globally. And you're sort of like, because this is a product in the hands of customers, you are forced to go through the long tail. You can't just do 95% and call it a day. We have to make this work. And so that long tail actually brings all kinds of interesting challenges. Recently, we were working quite a bit with speed limits as well. So speed limits don't just look like this. They come with lots of modifiers in all kinds of different countries. So sometimes you have speed limits that give you a minimum. And then in different countries, this minimum it's not specified that it's a minimum. It's specified by a different color, like say that it's in the blue background, or it has a line under it and stuff like that. So those all have to be read out by the system. And we have to, in a very sort of malleable way, be able to specify the ontologies for all these different signs, and in a very lightweight way, add all these possible attributes, all these possible detections. And so your data set is alive, and the labeling instructions are changing basically all the time. And in face of that, you have to curate this massive data set where you're encountering issues all the time. So it becomes kind of like a crazy challenge. Here's a bunch of other signs, speed limit signs in China, in Korea, in Japan, in Europe. For example, speed limits only are to be followed only in certain conditions, if it's wet on the road, in sharp turns and stuff like that. So it kind of gets out of crazy. Now, we curate not just the training sets, we curate the test sets and spend just as much time on those, if not more, because you want to make sure that your evaluation is really good. You can do arbitrary things on the training set, but you must have a really good evaluation because that gates your release into the world. So basically what I'm trying to get across is that it's a very difficult sort of domain because of the complexity of it. So this is slightly outdated numbers now, but I have a slide. Basically, we maintain roughly 48 networks in production. It's actually more now. They make roughly 1,000 distinct predictions. None of these predictions can ever regress. All of them must improve over time. It takes a long time to train these networks if you were to train them from scratch. Of course, we can get away with a lot of fine-tuning and things like that, and we do. But if you were to train this stack from scratch, it would train for a long time. So in one node, this would require an entire year to train. So how do you actually get this to work with also like not a very large team? So our team is not 500 people working on neural networks. It's more like a few dozen of really, really strong people on the team. And the way this works is we structure everything around the core infrastructure that we're building out. We're building out kind of like a general computer vision infrastructure in which it's very easy to curate data sets, create new types of tasks that fall into certain buckets. So maybe you want to create a new landmark task or a new segmentation task or a new detection task. You want to change the attributes around. You want to add an attribute and you want to get that to work. So everything we do, it's almost like we're on the meta layer of like, there's no, you're kind of working on a general recognition system. And then we have a huge team of not neural networks people necessarily, but say the labeling team or the PM team and so on that actually use that infrastructure and do all the heavy lifting. So I showed you that there's like 1 billion types of speed limits. You don't want to have neural networks engineers involved in that. You want them to create this general infrastructure that allows someone else to actually collect all these data to make it work. And to a large extent, we're finding that this is actually tractable and that we can actually create these generic computer vision systems that people can use to develop all these features and then deploy them on the car. So there's sort of this division going on, which I think is really interesting. So basically, automation is extremely important. The latency with which we deploy new features is extremely important. And we think of ourselves mostly as developing this core infrastructure, not actually like pursuing individual tasks like the stop sign detection task. That's not something that the neural network engineer would worry about. The neural network engineers work sort of about the segmentation prototype or the detection prototype, and that can work. And the active learning infrastructure for bubbling up these difficult data sets from the fleet. So far, I've only talked about image level predictions, and it's already quite crazy and involved and heavy. It gets even crazier once you actually go into the full self-driving stack. You can't just afford to do image level predictions and expect to actually drive on that. I think I sort of made this point, actually. I make a big deal out of the whole software 2.0 sort of like framework of looking at feature development because people don't look at neural network training as programming. To me, it's literally that you have feature demands, you have to make changes, you have to make errors, you have PRs. So you can borrow a lot of concepts. So basically what's happening in the team is when I joined, we had small neural networks doing some detections, and then these were stitched up in firmware in sort of the software 1.0 code, the C++ code, and so on. And basically the neural network stack has been taking on more and more of the functionality. Everything is becoming more and more end-to-end. So for example, we don't treat lane line detection as a segmentation task. You could. So you could, actually we have very few segmentation tasks, by the way, because like having segmentations on pixels isn't as easily amenable to driving. So it looks good on the image, but if you need to project it out and make a 3D sense of it, otherwise you can't drive through it. And that part is the hard part. So it's basically detecting these lane line markings individually and stitching them up is highly error prone. So you can just predict it out of the network directly. It works much better. Parked cars are parked not based on heuristics, but when the neural network says so. Cut-ins happen not based on any heuristics. They happen if a neural network says so, based on a lot of data, and so on. So for stitching up these environments, so we had to sort of basically like lay out the parking lot so that we can get Smart Summon to wind its way around to come to the person who's summoning the car. And you can imagine breaking this down into number one, curb detection task in these videos, and then stitching up these curbs in sort of the software 1.0 land, which would look something like this. We've developed this occupancy tracker that stitches up the image level predictions into a little map of the parking lot, and then we can see how this car is driving around to wind its way to the person. So this works to some extent, but you have to do the stitching, and the stitching is highly error prone across the camera seams and across time. So what we've been kind of working on is going much more toward these bird's eye view predictions, which are actually like relatively standard and well understood. But for us, it's kind of a step because of the history of the autopilot and how if you stick to the highway, you can actually get really far, even just paying attention to a single camera image that's forward-facing. We sort of have to compile up our stack from raw images. And of course, we don't have the LiDAR stack, so we have to stitch up the images into these bird's eye view predictions. But we don't have the occupancy tracker living in the C++ land. We now have the occupancy tracker living in a network. So individual views go through the cameras. We extract features. We have a fusion layer that does things like orthographic feature transforms and so on to put everything into, you have to re-represent image to space, and then you have to temporally smooth it. And that smoothing, again, is in a neural net. So we don't want smoothing in a C++ code base. You want smoothing sort of in the net. And then you have a decoder that gives you all the predictions. This is just a slide showing that I'm not going to go into too much detail of, I think, in interest of time. But basically, this works significantly better. OK, let me go into it briefly. So on the left, we see the ground truth of this intersection in terms of the road edges that make it up. On the right is what happens when you do a relatively good job, actually, of detecting the curbs in individual images, and then you project out the pixels, and it looks terrible. And then in the middle is what our bird's eye view networks would produce as a prediction that kind of just comes straight out of the net. And of course, these bird's eye view networks are not going to make really dumb errors like the one on the right, because they sort of have a sense of what these intersections can possibly look like and give you something sensible. So here I have a video that's showing sort of these predictions temporally over time, what that can look like. So we see that we have a pretty smooth intersection. On the left is basically the road edges that make up this intersection. Green are dividers, a bunch of attributes that I'm not going to go into. You can just imagine there's a lot of attribute detections that I'm not showing here. Here I'm showing a few more attributes showing coloring sort of the different parts of an intersection as we're going to turn through the left. Sort of like I mentioned, here's another one. Like I mentioned, basically we come up to these intersections for the first time always. So we don't actually know what these things look like. Is there a crosswalk? How many lanes are there? Where are the dividers? What is the connectivity structure of these lanes? Where are the traffic lights, stop signs, and so on? How do they relate? So which traffic lights control which lanes? Everything has to come out of the net, and it's a highly structured representation that we're sort of asking for in these cases. And it's quite hard to achieve, especially in the face of uncertainty. So if you're coming up to an intersection, you're really just staring at like a tiny sliver of this image in the middle at the horizon line, and you're trying to guess, is that 2 lanes, 3 lanes? You're not sure. What is the output of the net when you're not sure? Are you outputting multiple samples? If you're outputting samples that are crisp, then you need to track them. But if you're outputting not samples, but just like you try to produce rasters like I'm showing here, then you can have all these like mode splitting issues because the network is uncertainty and things become diffuse. So these are really like delicate, interesting challenges in terms of the raw neural network modeling, and they're hard to get right. But if you do get them right, again, in terms of scalability, that has large implications on your velocity. When we talk about like a global deployment of this technology on a world scale, because we don't have to pre-map everything in the world, which sounds like a lot of work, and keep it up to date. But the challenge, of course, is we are coming up to these arbitrary pieces, to these arbitrary geometries, and we have to solve for what that looks like. And so it's a very structured representation with a lot of uncertainty. And so I think this is kind of like the most interesting challenges for us right now in the team is how do you actually, in terms of the modeling approaches, predict these complex intersections. So for those of you who are maybe in academia and industry and so on, I would encourage you in terms of scalability for pushing autonomy forward. Do not assume that we can get away as an industry with HD LiDAR maps for global deployment of these features. I would take LiDAR maps and especially the flow of all the lanes and traffic and so on, and think about how can you predict an intersection without assuming a LiDAR map? What are the approaches here? Like, is there some kind of a, because these are, there's a set of lanes, and then these set of lanes can be controlled by a set of traffic lights. And all the pointer networks sort of that are necessary to actually make this work well and what they look like is highly not obvious, I would say. So we explore, of course, some of this in the team, but I think predicting these highly structured representations and dealing with uncertainty of them is a very interesting, deep technical challenge that I think academia can definitely contribute with. This is just a kind of an old video now showing that we apply this not just for static infrastructure, but we're trying to apply bird's eye view networks and representations to cars and objects, and of course how they move around. What is the assignment of cars to lanes? All these different things we of course have to know about so that we can anticipate how people are going to move through these environments. And yeah, I just have a slide here showing that this can get out of hand very quickly. The one nice benefit that you do have if you're trying to actually release this to the world is you are allowed to sort of know that you don't know in terms of like an actual product, right? You're not forced to handle every intersection as long as you come up to something and know that you can't handle it. You're allowed to sort of route your way around it, for example, and things like that. Because of the complexity of what these things look like in the world, I actually suspect we're going to have to go that kind of a route. So you're sort of allowed to not handle something, but you prefer to handle most things. But when you do handle them, you actually have to really do a really good job of it. Okay, so basically, that's roughly some of the kind of technical challenges that we're facing. Just to summarize, basically, for us, when I think about scalability and what's tricky and hard to get to work in terms of the kind of strategic landscape, and especially where Tesla finds itself, is number one, we are dealing with a massive scalability challenge around the finding of the needle in the haystack. And what this is referring to for us, haystack is the fleet. And you have cameras running at say 36 hertz, and there's 8 of them, and they're driving around all these interesting scenarios all the time. But you have to also catch the interesting scenarios so you can add them to your training set. So the haystack is kind of like all the cars navigating the world's, streets, and the needles are the tricky ones that actually make your network uncertain. And we need to find them, and we need to make sure we upload them, and we need to catch them. So this active learning to us is bread and butter of what we do. And you have to do this repeatedly, iteratively, and simultaneously across lots of labeling projects. And you, in order to be successful, because there's such a wide sort of a breadth of challenges, you actually don't want engineers in the loop. So the engineers are sort of designing the infrastructure for arbitrary tasks. And then the PMs and the labeling teams and so on are actually curating your the individual tasks. So that's kind of like how we try to approach it, but it's very tricky to develop this kind of infrastructure. Oh yeah, these are sort of examples. I have some examples of needles. So yeah, top left is a chair. This is not a render. This is not a simulation. This is not inserted by some GAN. This is a real thing. It's a needle, and we need to make sure that we catch it. And catching these needles is actually not trivial. So we've tried a lot of approaches with respect to using the entropy of different neural network ensembles trained with bootstrap sampling and things like that, and nothing like works really well, I think. So detecting basically that a network doesn't know and doing it efficiently at test time is kind of still an open problem in my mind. On the right, we have a person walking a dog. Here we have like mirrors. And here on the right, I'm showing toppled cones. But actually, they were recognized. The toppled cone in the far was recognized as a traffic light. It's a red traffic light. But of course, it's just a toppled cone. So these are the needles. And how you actually find needles in the haystack is kind of like the most interesting question to us. So if I was to pose this potentially to academia and how this can be worked on potentially is imagine giving yourself a data set of 50,000 examples, but actually only train on 10,000. Like basically you have to somehow incorporate the fact that I can label arbitrary image for some amount of cost. And I don't want to pay too much cost, but I need to label images because I know that that's kind of like the only certain way to actually get a neural network computer vision task to work is through labeling of images. There's a lot of less certain things that maybe don't work as well, work to some extent, but at least like the one sure certain way I've seen of making progress on any task is you curate a data set that is clean and varied, and you grow it and you pay the labeling cost. I know that works. There's a lot of exotic approaches as well through self-supervision, unsupervised learning, etc. But I think it's more hit and miss. So these are interesting questions for us. And number two, in terms of scalability, like I mentioned, these intersections get out of hand, and we need to actually, in a structured way, I think about how we can predict these complicated structured outputs so that we don't have to sort of represent them explicitly and maintain them over time, but we can actually get our neural nets to output them directly. And I think this is a very interesting challenge from a neural networks perspective.